Welcome to today's problem walkthrough. We're diving into problem number 2017, titled Grid Game.
In this session, we'll explore the problem, discuss possible approaches, and break down how to solve it step by step.
Let's get started.
In this problem, we have a 2xn grid, where each cell contains a certain number of points. The grid is represented as a 2D array called grid, where grid 0, I, corresponds to the points in the top row of the ith column, and grid 1, I, corresponds to the points in the bottom row of the ith column.
Two robots, Robot 1 and Robot 2, will traverse this grid. Robot 1 moves first, starting at the top left corner and ending at the bottom right corner, collecting points along its path. The constraint is that Robot 1 can only move right or down.
After Robot 1 completes its path, Robot 2 also moves from the top left to the bottom right corner, following the same movement rules, but it must avoid any cells visited by Robot 1. The challenge is that both robots aim to maximize the points they collect, but Robot 1, moving first, will strategically choose a path to minimize the maximum points Robot 2 can collect. The task is to return the maximum points Robot 2 can collect if both robots play optimally.
The output for this problem is a single integer, representing the maximum points Robot 2 can collect when both robots follow optimal strategies. Let's understand this with an example. Suppose the input grid is 2, 5, 4, 1, 5, 1. In this case, Robot 1 moves first and chooses the path grid 0, 0, grid 0, 1, grid 1, 1, grid 1, 2. Along this path, Robot 1 collects 2 points from grid 0, 0, 5 points from grid 0, 1, another 5 points from grid 1, 1, and 1 point from grid 1, 2. This totals to 13 points for Robot 1. Now, the cells visited by Robot 1 in grid 0, 0, grid 0, 1, grid 1, 1, and grid 1, 2 are blocked for Robot 2. This leaves Robot 2 with the path grid 1, 0, grid 1, 1, grid 1, 2. However, since grid 1, 1, and grid 1, 2 are already blocked by Robot 1, Robot 2 can only collect points from grid 1, 0, which is 4 points. Therefore, the output for this example is 4. In another example, consider the grid 3, 3, 1, 8, 5, 2. Robot 1 chooses the path grid 0, 0, grid 1, 0, grid 1, 1, grid 1, 2, collecting 3, 8, 5, and 2 points respectively, for a total of 18 points. The cells visited by Robot 1 in this case, grid 0, 0, grid 1, 0, grid 1, 1, and grid 1, 2, are blocked for Robot 2. This leaves Robot 2 with the path grid 0, 1, grid 0, 2, where it collects 3 points from grid 0, 1, and 1 point from grid 0, 2, totaling 4 points. Therefore, the output for this example is also 4. Now, consider a third example with the grid 1, 3, 1, 15, 1, 3, 3, 1. Robot 1 will choose the path grid 0, 0, grid 0, 1, grid 0, 2, grid 1, 2, grid 1, 3, collecting points 1, 3, 1, 3, and 1, which adds up to 9 points. The cells visited by Robot 1 in grid 0, 0, grid 0, 1, grid 0, 2, grid 1, 2, and grid 1, 3 are now blocked for Robot 2. This leaves Robot 2 with the path grid 1, 0, grid 1, 1. From this path, Robot 2 collects 1 point from grid 1, 0, and 3 points from grid 1, 1, totaling 4 points. The output for this example is 7. Finally, the problem comes with constraints and edge cases to consider.
The grid always has exactly 2 rows, and the number of columns can go up to 100,000.
Each cell in the grid contains between 0 and 100,000 points.
Edge cases include cases with the smallest grid size, such as 1, 1, where both robots can only move through one cell, or grids where all points are 0, resulting in both robots collecting 0 points. For larger grids with maximum values, the robots must carefully optimize their paths to minimize Robot 2's score.
To tackle the grid game problem, the first approach we consider is the brute force simulation.
The intuition here is straightforward. Player 1 can start from any column in the top row, and we then simulate player 2's optimal response to maximize their own score in the bottom row. By evaluating all possible starting columns for player 1, we calculate the resulting scores and identify the minimum score player 1 can achieve across these scenarios.
However, this approach is computationally expensive.
For each of the n columns player 1 might choose, we simulate player 2's response, leading to an n² time complexity. This makes the brute force method impractical for large grid sizes, especially when n can go up to 10 to the power of 5. To overcome this limitation, we consider an optimized approach that leverages the concept of prefix and suffix sums. The key insight is that instead of simulating all possible moves, we can calculate player 2's potential maximum score for each of player 1's choices in constant time using pre-computed sums. This provides a more efficient way to solve the problem while maintaining correctness. Now, let's dive deeper into the prefix and suffix sum optimization.
The first step is to compute the prefix and suffix sums for both rows of the grid. The prefix sum at any column I represents the cumulative sum of all elements from the start of the row up to column I, while the suffix sum at column I gives the cumulative sum from column I to the end of the row. With these pre-computed sums, we can make a crucial observation. If player 1 chooses column I, player 2's maximum possible score will be the larger of two values, the sum of elements in the top row to the right of column I, which is derived from the suffix sum, or the sum of elements in the bottom row to the left of column I, which comes from the prefix sum. By iterating through all columns, we compute player 2's maximum score for each choice player 1 might make and then track the minimum of these maximum scores. This approach is computationally efficient.
Computing the prefix and suffix sums takes n time, and iterating through the columns to calculate scores also takes n, resulting in a total time complexity of n. This efficiency makes the prefix and suffix sum method highly suitable for large grids. The chosen strategy for solving this problem is the prefix and suffix sum optimization. There are several reasons why this approach stands out. First, it is far more efficient than the brute force method, reducing the time complexity from n² to n. This makes it feasible to handle the problem's constraints, where n can go up to 10 to the power of 5. Additionally, the implementation is relatively straightforward. The prefix and suffix sums are easy to compute, and the logic for determining player 2's maximum score is intuitive. From a scalability perspective, this method is well suited for large inputs, ensuring the solution remains performant even with the largest allowed grid sizes.
However, there are trade-offs to consider.
While the brute force approach is conceptually simple, it is computationally prohibitive for large grids. On the other hand, the prefix and suffix sum optimization involves slightly more complex logic and pre-processing, but this trade-off is justified by the significant performance gains. By leveraging the efficiency of pre-computed sums, this strategy ensures that player 1's optimal moves can be determined quickly and effectively, making it the best choice for this problem. In this problem, we are tackling a grid-based game involving two players who take turns making moves to maximize their respective scores. The grid is a 2D array with two rows, the top row, where player 1 begins, and the bottom row, which is player 2's domain. Player 1 starts by choosing any column from the top row, and from there, player 2 will strategize to minimize player 1's score while maximizing their own. The challenge lies in determining the maximum score player 1 can achieve, assuming player 2 plays optimally. To approach this, we first need to clearly understand the structure of the grid and how the moves are made. Player 1 has the freedom to start in any column of the top row, while player 2's responses are designed to counter player 1's choice and minimize their score. The key decisions revolve around player 1's starting column and player 2's optimal countermove, making this a strategic problem where both players aim to outsmart each other within the given constraints.
To address the problem, we can begin with a brute force simulation.
This involves testing all possible moves player 1 can make and evaluating player 2's optimal responses.
Specifically, player 1 starts by selecting a column J in the top row.
For each choice of J, we simulate player 2's response, where they aim to maximize their own score by choosing the best possible column in the bottom row.
After player 2 makes their move, we calculate the resulting score for player 1.
By iterating through all potential starting columns for player 1 and tracking the results, we can identify the maximum score player 1 can achieve under these conditions. The steps to implement this brute force approach begin with initializing variables to keep track of player 1's maximum score, and then iterating over each column in the grid to simulate the outcomes. For each column J chosen by player 1, player 2's optimal response is calculated by considering the sum of values in the bottom row while excluding the column chosen by player 1. Player 2's goal is to minimize player 1's resulting score, so the strategy involves subtracting player 2's optimal score from the total score in the grid.
This gives the resulting score for player 1.
To ensure robustness, we also handle edge cases such as when there is only one column in the grid or if the grid is empty. The pseudocode implementation reflects these steps, iterating through each column in the top row to compute player 1's potential scores. By evaluating all possible moves, we can determine the maximum score player 1 can achieve after accounting for player 2's optimal strategy.
The problem highlights several key insights. First, player 2's strategy is to always choose the path that maximizes their own score in the bottom row, which indirectly minimizes player 1's score.
To maximize their score, player 1 must evaluate the impact of player 2's optimal play for every potential starting column. The symmetry of the grid simplifies the analysis, as we only need to consider the interaction between two rows. In terms of data structures, we use the 2xn matrix to represent the grid and a simple variable to track player 1's maximum score. The brute force approach is efficient for this problem due to the grid's small size, with a time complexity of O(n) arising from iterating over all columns. The space complexity is minimal, as the calculations rely on a few variables without requiring additional data structures.
Optimizations can further improve the efficiency of our approach.
By pre-computing prefix and suffix sums for both rows of the grid, we can reduce redundant calculations when determining player 2's optimal response. This optimization allows us to calculate player 2's score in constant time for each column, keeping the overall time complexity linear. With these improvements, the solution becomes both efficient and scalable, ensuring that we can handle the problem effectively while maintaining clarity and simplicity in the implementation. Here, we begin by defining a function called gridGame within the solution class, which takes a 2D grid as input. The goal is to compute the minimum score player 2 can leave for player 1 after both players take their optimal moves. To start, we calculate prefix sums for both rows of the grid, which will help us efficiently compute the sums of subarrays later.
We initialize two arrays, top_prefix and bottom_prefix, to store the prefix sums for the top and bottom rows, respectively.
The length of these arrays matches the number of columns in the grid.
Next, we populate the top_prefix array. The first element is simply the value in the top left cell of the grid. For subsequent columns, each entry in top_prefix is the cumulative sum of all values in the top row up to that column. Similarly, we calculate the prefix sums for the bottom row using the bottom_prefix array, where each element stores the cumulative sum of the bottom row values up to that column. With these prefix sums, we can efficiently calculate remaining sums for both rows as player 1 makes their move at each column in the next step. Now, we focus on determining the minimum score player 2 can leave for player 1. We initialize result to infinity, representing the best possible outcome for player 1.
Then, we iterate through each column to simulate player 1 making their move at that position.
For each column, we calculate the remaining sums of the top and bottom rows. The top_remaining value represents the portion of the top row that player 2 can still access after player 1's move. Similarly, bottom_remaining represents the accessible portion of the bottom row before player 1's move.
If player 1 starts at the first column, bottom_remaining is 0 since there are no columns to the left. Player 2 will always choose the maximum of these two values to maximize their own score. We then update result to the minimum of its current value and player 2's score, ensuring we find the smallest possible score player 2 can leave for player 1. Finally, we return result as the answer, which represents the minimum score player 2 can achieve while playing optimally. Here, we start by importing the necessary packages and defining our solution class with the method gridGame. The input to this method is a 2D grid, and we first determine the number of columns, n, which is key to iterating through the grid.
To optimize the solution, we calculate prefix sums for the top and bottom rows of the grid.
These prefix sums help us quickly determine the cumulative sum of elements up to any column, significantly reducing redundant calculations during the process. For the top row, we initialize the first element of top prefix with the value at grid 0, 0. We then iterate through the remaining columns, incrementally adding the current column's value to the prefix sum from the previous column. Similarly, for the bottom row, we initialize bottom prefix 0 with grid 1, 0 and compute the prefix sums for the rest of the row. This prefix sum computation sets the foundation for efficiently determining the sums of sections in the grid later. Next, we define a variable result to store the minimum score that player 2 can leave for player 1. We initialize it with the maximum possible value to ensure any calculated score will be smaller. Finally, we loop through each column, simulating player 1's move and calculating the remaining sums for both rows after player 1 has chosen a column. At this point, we're ready to analyze how player 2 can maximize their advantage. For each column chosen by player 1, we determine the two potential paths player 2 can take, the remaining values in the top row after player 1's move, and the cumulative sum of the bottom row up to the column before player 1's choice. The top remaining value is calculated using the total sum of the top row minus the prefix sum at the chosen column, while bottom remaining is derived from the prefix sum of the bottom row, considering only the columns before player 1's choice. If player 1 selects the first column, bottom remaining is set to 0 since there are no columns before it. Player 2 will always choose the path that maximizes their score, which we calculate using math.max, top remaining, bottom remaining. Then, we update the result variable by taking the minimum of its current value and player 2's score for this move. This ensures result always holds the smallest possible score that player 2 can leave for player 1 across all scenarios. Once the loop completes, we return the result as an integer. This value represents the optimal score player 2 can ensure for player 1 in this grid game, effectively solving the problem. Here, we start by analyzing a simple example with the grid provided. The grid has 2 rows and 3 columns, so n equals 3. Our first step is to compute the prefix sums for both rows. For the top row, we calculate the cumulative sums as follows. The first value is simply the first cell, 2, the second value is the sum of the first and second cells, giving us 7. The third value is the sum of all 3, resulting in 11. This gives us a top prefix array of 2, 7, 11. Similarly, for the bottom row, the first value is 1, the second is the sum of the first 2 cells, which is 6, and the third is the total sum of 7. This results in a bottom prefix array of 1, 6, 7. With these prefix sums calculated, we can now evaluate the possible moves player 1 can make to minimize player 2's maximum score. To evaluate player 1's moves, we iterate over each column, calculating the scores for player 2 under the assumption that player 1 stops at that column. For column 0, the top remaining sum is the total of the top prefix minus the value at column 0, which is 9. The bottom remaining sum is 0 since player 1 hasn't touched the bottom row yet. Player 2's score is the maximum of these two, which is 9, and the result is updated to 9. For column 1, the top remaining is 4, while the bottom remaining is 1. Player 2's score is the maximum of these, 4, and the result updates to 4 as it's smaller than the previous result. Finally, for column 2, there is no remaining top sum, and the bottom remaining is 6. Player 2's score becomes 6, but the result remains 4 as it's the minimum so far. The final result for this example is 4, which represents player 2's minimized maximum score. Now we move to a larger grid example with 4 columns. The prefix sums are calculated similarly to the previous example. For the top row, the prefix sums result in 3, 6, 16, 18, and for the bottom row, 1, 2, 3, 23. As before, we evaluate player 1's moves by iterating over each column. For column 0, the top remaining sum is 15, and the bottom remaining is 0. Player 2's score is 15, and the result starts at 15. This process will continue for the subsequent columns to refine the result further. For column 1, the top remaining sum is 12, while the bottom remaining is 1. Player 2's score is the maximum of the two, which is 12, and the result updates to 12. For column 2, the top remaining sum drops to 2, and the bottom remaining is 2 as well. Player 2's score is 2, and the result updates to 2 as it's smaller than the previous result. Finally, for column 3, there is no remaining top sum, and the bottom remaining sum is 3. Player 2's score here is 3, but the result stays at 2 since it's already the minimum.
The final result for this example is 2, representing the optimal minimized score for player 2.
In this edge case example, we have a smaller grid with only 2 columns. The prefix sums for the top row are 1, 4, and for the bottom row 1, 2. Evaluating player 1's moves, we start with column 0.
The top remaining sum is 3, and the bottom remaining is 0.
Player 2's score is the maximum of these, which is 3, and the result starts at 3. We then proceed to evaluate the remaining columns to find the minimum result. For column 1, the top remaining sum is 0 since player 1 has already collected all the top row values.
The bottom remaining sum is 1.
Player 2's score is, therefore, 1, and the result updates to 1 as it is smaller than the previous value. With no more columns to evaluate, the final result for this edge case is 1, which represents player 2's minimized maximum score.
To analyze the time complexity of this solution, let's break it into its key components. First, we calculate the prefix sums for both rows of the grid. Since the grid has 2 rows and n columns, iterating through each row takes n time. With 2 rows, this step totals 2 n, which simplifies to n. Next, the algorithm iterates through each column to compute the possible scores for player 2 based on player 1's move. For each column I, we calculate values like top_remaining, bottom_remaining, and player 2_score. These are simple arithmetic operations, each performed in constant time, or O1. Since we process all n columns, the total cost of this step is n iterations, each requiring O1 work. Finally, the result is updated for each column, which also takes constant time per iteration, contributing an additional O1 per column. All these steps together form the basis for the overall time complexity. Adding up the time complexities from each step, we have n for prefix sum calculations and another n for column iterations. Summing these gives us a total time complexity of n plus n, which simplifies to n. Now, let's consider the space complexity.
The input grid itself has 2 rows and n columns, but since it's part of the input, its space is not included in the additional space complexity.
We then have 2 arrays, top_prefix and bottom_prefix, each of size n, to store the cumulative sums for the top and bottom rows. These arrays require n space in total. Additionally, we use a constant amount of space for variables like n, result, top_remaining, bottom_remaining, and player 2_score, all of which require O1 space. Combining these components, the additional space used by the algorithm can now be analyzed.
The total space complexity comes from the n space required for the prefix sum arrays and the O1 space for auxiliary variables. Together, this sums to n plus O1, which simplifies to n. Comparing this solution to a brute force approach highlights its efficiency. A naive method would involve simulating all possible paths for both players and explicitly calculating their scores. This would require enumerating all possible splits across the grid, leading to an exponential time complexity of 2 to the power of n. In contrast, our optimized solution leverages prefix sums to efficiently calculate player 2's optimal score for each potential move of player 1. This reduces the time complexity dramatically to n, while maintaining the same space complexity. Importantly, this algorithm's structured processing ensures that its performance remains consistent across best, average, and worst cases. Whether the grid values are highly varied or uniform, the time and space complexities remain n. To formally establish the n time complexity, let's examine the operation step by step. Computing the prefix sums requires iterating through each row once, which is clearly n. Similarly, iterating through the columns involves n iterations, and since each iteration consists of constant time calculations, this step is also n. Because these are sequential operations and not nested, their total cost is the sum of their individual complexities, n plus n, which simplifies to n. On the space complexity front, the 2 prefix sum arrays dominate with their n space requirement, while all other variables contribute only O1 space. The total additional space is therefore n. Together, this proves that the algorithm is both time and space efficient, with linear complexity in both dimensions, making it well suited for large grids. One common mistake when solving grid-based problems is ignoring edge cases. For example, scenarios like empty arrays, grids with only one row or column, or grids where all elements are identical are often overlooked. These edge cases are critical because they can expose flaws in how boundary conditions are handled or highlight incorrect assumptions about the input.
Another frequent issue is overcomplicating the brute force approach.
The purpose of brute force is to ensure a clear understanding of the problem constraints and verify the expected outputs, not to optimize the solution at this stage. Adding unnecessary complexity can make debugging harder and detract from the learning process. Finally, a significant challenge in dynamic programming, DP, is defining the correct state transitions.
Misidentifying relationships between states or errors in the recurrence relation can lead to entirely wrong results.
Since DP relies heavily on these transitions, even minor inaccuracies can have major consequences for the solution's correctness.
Another pitfall to watch for is forgetting to optimize space in dynamic programming.
Many people default to using a full 2D matrix to store intermediate results, even when only the current and previous rows or columns are necessary.
This approach wastes memory and can cause your solution to exceed memory limits for larger inputs.
Optimizing space by using rolling arrays or similar techniques is key to solving these issues.
Additionally, it's important to avoid premature optimization.
Jumping directly to advanced techniques like greedy algorithms or other shortcuts without first ensuring correctness can lead to solutions that only work in certain scenarios.
It's always better to validate your solution comprehensively before attempting to optimize it. Correctness should always take precedence over efficiency in the early stages.
When approaching these types of problems in an interview setting, it's essential to focus on problem decomposition. Start by clearly explaining the brute force solution to demonstrate your understanding of the problem, and then transition to more optimized approaches like dynamic programming or greedy methods.
Highlight the trade-offs between space and time complexity as you refine your solution.
For example, reducing space complexity from O(n) squared to O(n) by using rolling arrays shows both efficiency and resourcefulness.
Also, make it a point to think aloud.
Sharing your thought process as you move from the brute force approach to an optimized solution provides insight into your problem-solving skills. Don't forget to discuss how your solution handles scalability, particularly for large inputs and edge cases, as this showcases the robustness of your approach. To deepen your understanding, explore related problems such as LeetCode 64, which focuses on minimum path sums, or LeetCode 221, which deals with optimizing space in a grid-based problem. These examples can provide additional insights and strategies for tackling similar challenges.
Alternative approaches can sometimes be applicable to grid-based problems, depending on the constraints.
For instance, greedy algorithms might work well under specific conditions, but they often fail to guarantee a globally optimal solution. While they may be faster, it's crucial to prove their correctness before relying on them.
Recursive backtracking with memoization is another option, especially when trying to derive the recurrence for a dynamic programming solution.
However, this method tends to have higher recursion overhead and may not be as efficient in terms of time.
Lastly, understanding the trade-offs between bottom-up and top-down dynamic programming is important. While top-down approaches with memoization are often more intuitive, bottom-up DP tends to be more space-efficient.
This efficiency comes at the cost of requiring a solid grasp of initialization and base cases.
Choosing the right approach depends on the problem's specific requirements and constraints.
That wraps up our discussion on problem number 2017, Grid Game.
We covered the brute force approach and discussed its implications. Keep practicing grid-based problems to improve your problem-solving skills. Thanks for watching, and see you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!